photons coming off the sun, right? Okay, so the pressure of the solar radiation is pushing that stuff off, evaporating this thing. Comets' tails get longer when they're closer to the star, shorter when they're farther away, and presumably when they're way the hell out, in the Oort cloud or whatever, they'd have no tail at all. The star, when they're at the far end of their orbit, the sun only looks like a bright star in the sky, right? So their orbit is incredibly elliptical. They spend most of their time out here. Every now and then, for a few exciting moments, they dart down through the inner planets and then go back up, right? Okay. Yeah.
What's the radius of Pluto in astronomical units?
I've got a chart of that. It's hundreds.
Hundreds?
Yeah.
So 50,000 would be quite a bit.
Way the hell and gone, yeah. Yeah.
What is a shooting star?
Shooting stars are actually chunks of stuff that hit the Earth's atmosphere, right? So a chunk of ice. So sometimes we go through the trails of comets, right? So like the one that you see in what's it called in August? No, what are the meteor shower? Perseids? Perseid? Yeah. Those meteor showers are when the Earth's orbit passes near the trajectory that a comet takes, right? So the comets are dropping off chunks of ice in their trail, in their path, and we just go through that, right? It could also be chunks of rock, like asteroids that cross our orbital path, right? And if you read The Brief History of Nearly Everything, Jordan Raffo, okay, they talk about this. There's a place in Iowa where there's a meteor impact crater. It's been filled in, but I can't remember what the details are, but it's like a mile deep and miles across like this, right? A chunk of rock came from outer space and just punched a hole in the Earth's crust, and it's now been filled with glacial till, so you can't tell it's there unless you're a geologist and you do clever things, right? And Bill Bryson takes great delight, because he reads the books on tape version of it, he takes great delight in saying there will be absolutely no warning of this whatsoever. We don't even know when they would occur. It's like 1 minute you're there, the next minute you're a crater miles deep in the Earth's crust, right? This is our solar neighborhood. If we back out, the sun and you and me and all the stars that you can see are moving at 1 million miles a day in an outer spiral arm at 40,000 miles per hour in a galaxy we call the Milky Way. This is the sun and you and me and all the stars that you can see. All these stars are Milky Way stars. So Sirius and Procyon and Alpha Centauri and Proxima Centauri. Right? And we are right here. This is the solar system right here. And we are right above that center spot there. Notice that the closest star is something less than 5 light years away, about 4.3. Yeah?
I was just wondering, how do we take pictures of our own galaxy?
We don't. All of these things are just like artist renditions, right? Our own galaxy is the one thing we can't see, right? Isn't that sad? No mirror out in space. There is a project that they're going to do to send a mirror off into space so we can see it, but that won't be ready for another 50,000 years. So I'm just kidding. If it moved at the speed of light, yeah.
Where is it that one that says BC?
Oh, here, A, B, and C. They just name them. They're not terribly imaginative in how they name them,
And,
right?
One of the things that's supposed to happen in 2012 is the solar system and the Milky Way are in alignment or something.
Yeah.
Do you know anything about that?
Yeah, and the neutrinos are going to mutate and cause the Earth's crust to explode, right? Isn't that right?
I don't know.
Yeah.
Maybe.
No, I don't know about that, but it's probably not going to be a huge problem, right?
But is it actually going to be lined up?
Maybe. Yeah, I don't know. It could be. I'm not too worried about this, but anyway, suffice it to say that the bright stars that we see, like Sirius is one of the brightest stars, these stars are maybe a few hundred light years from Earth. This is 20 light years. These are the close stars. But other stars are a few hundred light years from Earth, the ones you can see. The North Star is 600 some light years. So we're talking about stars you can see in the sky are Milky Way stars, and they are hundreds to maybe 1,000 light years away. Yeah? Okay. And now we're talking about galaxies. Notice that these are called nebula. I will never call them nebula, that's my promise to you. Nebula is an old term. Nebula just means something that's nebulous, yes? A foggy patch in the telescope, okay? These things, since 1921, this is a historical reference, since 1921, the Mount Wilson Observatory, right? We now know that these are galaxies just like the Milky Way galaxy. So spiral nebula means an elliptical nebula, right? what they're talking about are galaxies just like our own galaxy, okay? And I'll never call them that, but that's just an historic term. They might call them that in an IB test. Like discuss the redshift of spiral nebula, right? Well, that's what they thought they were, but of course they weren't, right? Okay. There are elliptical ones. These guys are basically elliptical, seen from any direction, right? Okay. So they are just like basically like bees buzzing around a hive. There's no real pattern. These guys, though, all like the spirals lie in a plane. Okay. These guys lie in a plane. Barred spirals have a little bar like that. Okay. Although some barred spirals, and I'll show you, kind of look like elliptical galaxies depending on how you see them. But there's a really good way to tell the difference, a surefire way to tell the difference between a spiral galaxy and a barred spiral that I'm going to show you. I've got a slide of it. It's really quite good. Okay. But basically, barred spirals look like you could stick a screwdriver in, right? No Phillips head type barred spirals where you can stick a Phillips screwdriver in, which, again, there we have it. Right? So these are Hubble types of galaxies. Here are more pictures. Elliptical are boring. They represent, by the way, we think galaxies when they're born are all spiral types, and that they evolve through collisions and entropic situations. They turn into elliptical galaxies, right? And here's a barred spiral. Again, it's hard, is that a barred spiral or a normal? Some normal ones just look like cow pies, right? It's like schwupped up, right? But it's got that little bar. Again, there's a really good way to tell the difference between a barred spiral and a not a barred spiral, a normal spiral, right? Then this is my favorite. There are irregular galaxies too, right? And don't confuse those with peculiar, right? Can't you just see these guys sitting around? What do you think, Earl? Is that irregular, or peculiar? Oh, I'd say it's definitely peculiar. No, it's irregular. Can't you see them arguing that finer point there? I really don't know. Definitely, it's very peculiar. I'd say this is one's more peculiar. Just let whatever that was that you unleashed on that last test we took, just unleash it on that question. If it's ever asked of you, just, go to great depths, write volumes about irregular versus peculiar, okay? Because Lord knows I don't know, okay? Okay? Here is, if this were the Milky Way galaxy, right, then we are, it's 100,000 light years side to side, right? It bulges in the middle, 16,000 light years thick, but out by us it's just 3,000 light years wide, okay? I know. There we go, right? Okay. Our galaxy itself contains 100 billion stars. It's 100,000 light years wide, side to side. Bulges in the middle, 16,000 light years thick, but out by us it's just 3,000 light years wide. So we're 30,000 light years from galactic central point. We go around every 200 million years, right? So if this is 50,000 light years and we're 30, then we're 3/5 of the way out. We're kind of in the middle of the arms, right? We're an ordinary size star on an ordinary size galaxy. Yeah? That's kind of crazy. Isn't that crazy? Okay. And then notice that there's 100 billion stars. Well, this is kind of cool. The mass of the sun is about 3 × 10⁻30 kilograms. If you divide the total mass of the Milky Way with the number of stars, you get about the mass of the sun. So we're an average size sun. Isn't that crazy? Right? And then, let's leap ahead. In the visible universe, there are about 100 billion galaxies, on the order of 100 billion galaxies, each containing 100 billion stars. Yeah? Right? That's like a lot, right? And then let's make us feel even smaller. Let's feel even smaller. Are you ready for this? The part of the universe we can see is to the whole universe we think as a proton is to the planet Earth. There we go. Yeah. And what are we talking about? Well, we're talking about expansion and inflation, Big Bang Theory, right? The part we can see is such a small part, and the reason why we think it's so small is this, right? Does this part of our Earth look round? Does it look round? No, it doesn't look round. The Earth is locally flat, globally round, yes? So if you look at only a small part of the Earth, it looks flat, yes? Okay, so the part that we can see all the way to the edge of our ability to see, right, all the way back to the Big Bang, is as flat as can be. Right? So if it has the curvature we think it has, through other reasons, then it must be really big, because we're not seeing any of that curvature at all in the part we can see. I know, I hate that, right? The edge, and what's beyond that? Cheese. After that, more cheese, yeah. Because of expansion rates and other things, right? But they're examining that, right? There's a lot of I don't know, I think he did. Okay. That's right.